your boy JOHHABRAHIM. What are we gonna do today? We're gonna look into organic chemistry for 1 hour. Wait, 1 hour? That's too low. Okay. No, don't say okay. That's too low. You can't do shit with 1 hour. Okay. No. Okay. Discord. Here I come. So, recently I did start reading a book, not recently, yesterday. I did look into a book for organic chemistry. It was from Clayton Claperon or something, and it had some. Let me pull that up. It was here. It had the uh, required organic important structures to learn, like side chains. We got, yep. I don't know if it's visible. It's now visible. Okay. Let's do this. Is it visible now? Yep, it is. So these are the organic structures that you gotta learn. You gotta learn. At least I got him. So I'm gonna start with writing these into my notebook, and then I continue with the normal notes. You understand? No? Okay. That's how at least one person in this world is gonna sound similar to. Oh, the creaking noise, bro. Bing, 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 bing. No, this is the one. This the one. This the one. Which Conmingo. Is it? Okay, what are these? Hey Siri, set a timer for 10 minutes. Oh fuck, okay. Okay, cloud is better. Sonnet 4.6, 3.5, okay. So I'm wondering, should I continue with you or should I go back to chat GPT? Do you think you are better in providing accurate answers? Okay. I'm slowly gonna stop using ChatGPT. I don't know why, a lot of reasons. So the last This is the first page we are starting, and can you explain more on the topics that I'm seeing here. The core idea is simple. Different types of radiation interact with molecules in different ways, and by measuring those interactions, we can figure out the molecule structure. Think of it like this: each technique gives you a different clue about the molecule, of course. Okay, I get it. Five techniques, what each one tells you. X-ray diffraction uses X-ray scattered off a crystalline solid. Gives you the most complete picture, exact bond length, bond angles, 3D shape. Downside, the molecule needs to form a crystal, which isn't always possible. X-ray. No, oh, not like that. X-ray. Wavelength. Where is X-ray? It's a high. Okay. So X-rays are high frequency. UVV spectroscopy. Ultraviolet or visible light interacts with valence electrons. When a molecule absorbs this light, electron jumps to a higher energy level, most useful for molecules with conjugated system. Alternating double bonds or aromatic rings tell you something about the electronic structure but not full detail. IR spectroscopy, infrared. Infrared light causes bonds to vibrate and rotate. Different functional groups absorb at characteristic frequencies, great for identifying functional groups. Think of it as a functional group detector. Okay? NMR spectroscopy, radio waves interact with atomic nuclei. In a magnetic field, it tells you how many hydrogen carbons there are, what environment they're in, and how they're connected. The most powerful technique for figuring out full molecular structure. You'll spend a lot of time on this one. Okay. Mass spectrometry. Technically not spectroscopy. No waves of light involved. So spectroscopy involves waves of light. Spectrometry, molecules is ionized and fragmented. Then you measure the mass of the pieces. Tells you the molecular weight and can help identify the molecular formula. Fragmentation pattern also gives structural clues. Mass spectroscopy. No, spectrometry. Mass spectrometry, how molecular weight and formula. Infrared spectroscopy, what functional groups. So IR is for functional groups, UVV is for conjugated aromatic system. In the MAR, how are the atoms connected? Radio waves interact with atomic nuclei. Radio waves in a magnetic field tells you how many hydrogen carbon there are, what environment they are in, and how they are connected. Okay, I need to know more on how this works, especially NMR. I kind of forgot. I remember looking into it, but I need to look into it again. Your notes correctly point out that MS is not true spectroscopy. Mass spectroscopy, spectrometry, right? Mass spectrometry, not spectroscopy. Spectroscopy means interaction with electromagnetic waves, while works on physically breaking apart and weighing molecules. It's grouped with these techniques because it serves the same purpose. Structure determination, not because it works in the same way. Okay. Okay. Now, I have some question starting with X-rays as them being what? A high frequency wave. And could you care to explain why this high frequency QU wave is good? Whoa, good at. Or the best at the structure, etc. And also I'm confused on the NMR, like on how (10 minutes). Also, I'm confused on the IR, figuring out how we are able to observe the vibration slash rotation. Are we inducing that movement or just observing the movement that already exists? Great questions. Shut the fuck up. Why high frequency X-rays are best for structure. Frequency and wavelength are inversely related. High frequency, very short wavelength. X-rays have wavelength of around 1 nanometer, which is roughly the same size, as the distance between atoms in a molecule. Bond lengths, okay. So it's like a. Okay. Oh, whoa. I don't gotta push that. Wait, push ups, right? Push, 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 push ups. Push ups. Wario. 10. Diamond. What? Extra, okay, this is the key insight. To see something, your wave needs to be about the same size as what you're looking at. Think of it like this: if you throw ocean waves at a tiny pebble, the waves just pass around it and you learn nothing. But if you throw ripples the same size as the pebble, they scatter and you can detect the shape. What? What? The ripples the same size as the pebble, they scatter. Okay, I need more on this. I need more explanation on this. So visible light waves are way too big to detect individual atoms. X-rays are just right size to interact with atomic position. When X-rays hit a crystal, they scatter off the electron cloud around the atoms. The pattern of scattering, called diffraction pattern, is mathematically decoded to give you exact atom position, bond length, and angles. Why crystals though? Because you need a millions of molecules all lined up in the same orientation to get a clear, strong diffraction signal. One molecule alone gives too weak a signal. How NMR works. This one builds a few ideas step by step. Nuclei have spin. Certain atomic nuclei, especially hydrogen and carbon 13, behave like tiny magnets because they have a property called nuclear spin. Normally, this Normally these tiny magnets point in random direction. Apply a strong magnetic field. When you put the molecule in a powerful magnetic field, the nuclei line up either with the field or against the field, like a compass needle aligning with Earth's magnetic field. Hit it with radio waves. Then you fire radio waves at the molecule. When the frequency of those radio waves exactly matches the energy gap, when the frequency of the radio waves exactly match the gap between the two spin states, the nucleus absorbs the energy and flips from the low energy state to the high energy state. This is called resonance. That's where the name comes from. Mhm. The environmental matters. Here, the clever path, the electron surrounds each nucleus slightly shielded from external magnetic fields. So nuclei in different chemical environments next to CO versus next to CH, for example, experience slightly different effective magnetic field and therefore absorb radio waves at slightly different frequencies. This difference is called chemical shift, and now it's how NMR tells apart different hydrogen or carbon in a molecule. In short, each unique hydrogen carbon out in the molecule absorbs a slightly different frequency. The patterns of absorption tells you what chemical environment oh, each chemical environment each atom is in. From that you can piece together the whole structure. The pattern of absorption tells what chemical environment each atom is in. From that you can piece together the whole structure. Your IR question: are we including vibrations or just observing it? This is a really good question. The answer is both. In a sense, we're inducing a change. Here's the truth: bonds are already vibrating constantly at room temperature. You're not turning vibrations on. Molecules are always wiggling, bond strength stretching and bending all the time due to thermal energy. So what does IR actually do? IR light comes in and the frequency matches the natural vibration frequency of a particular bond. When this happens, the bond absorbs the IR energy and vibrates more intensely. The molecule jumps from a lower vibrational energy level to a higher one. Think of it like pushing a child on a swing. But there's one condition for the IR absorption. Not every vibration absorbs IR light. Not every vibration absorbs IR light. The vibration must cause a change in the dipole moment of the molecule. This means the bond needs some polarity, one end more positive and one end negative. The vibration needs to change that charge distribution. Absorb IR strongly, very polar bond, very big dipole change. OH stretches, absorb IR strongly polar and gives a bold peak, bond peak. Symmetric CC bonds in some molecules do not absorb IR, no dipole charge change. Okay, here we are introducing the H and C molecules to the magnetic field, and after that hitting them with radio waves. I kinda get it. but where is the sample? Or where will the sample that we wanna measure? NMR is for aromatic ring, right? No, to measure how are the atoms connected part. Stop. Wave bevel analogy, deep explanation. Let me make this concrete with progression. Imagine you're blind and you want to figure out the shape of an object in front of you. You have two choices: throw bowling balls at it, throw marbles at it. If the object is tiny, bowling balls just knock it aside and miss entirely. Yeah. You get no useful shape information, but marbles get closer in shape, bounce back patterns, okay? Waves work the same way. The key rule is wave can only detect or interact meaningfully with an object that is similar in the size of its wavelength, okay? A bond between two carbon atoms is 0.15 nanometers. Long X-rays have wavelengths right in that range, so they interact with the atomic position and scatter off them. Visible light waves are thousands of times larger than a bond, so they just pass through as if the atoms are even there. What scattering actually looks like: when the X-rays hit the electron cloud around the atom, they bounce off in a new direction like billiard balls. In a crystal, millions of the molecules are perfectly aligned, so all these scattered waves add up in a specific direction, constructive interference. No, it's for IR, right? X-ray. The physical setup: you take a compound and dissolve it in a special solvent, usually CdCl3, deuterated chloroform, which doesn't interfere with the measurement. You put the solution into a thin glass tube, NMR tube. That tube is inserted into a giant superconducting magnet. The machine itself, the magnet aligns all the H and C13 nuclei in your sample. Okay, so first off, I don't know if all the organic compounds have a C13. A radio wave pulse hits the sample, the nuclei absorb and re emit radio signals that, as they relax, these signals are detected and converted into a spectrum you read. So the sample is literally sitting inside the magnet and the whole time. Now, to your real question, how does this tell us how atoms are connected? Here's the key concept: electrons shield the nuclei from magnetic field. Electrons shield nuclei from magnetic field. Okay. Mhm. Well, ba-da-bum bum ba-dum ba-ba. Did I set a timer? No, I did not. Idiot. Idiot. Dun, 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 dun. It's working. Okay, that's good. Hey Siri, set a timer for 20 minutes. Hey Siri, set a timer for 10 minutes. Well, electrons shield nuclei from the magnetic field. Every hydrogen in your molecule is surrounded by electrons. These electrons slightly push back against the external magnetic field, so each hydrogen feels slightly weaker fields than the machine is actually applying. The nucleus is gonna. Okay. Now, here's where connectivity comes in. A hydrogen sitting next to an electronegative atom like oxygen has fewer electrons around it. Oxygen pulls them away, so it feels more of the magnetic field it absorbs at different frequency than the hydrogen sitting on a plain carbon chain far from an electronegative atom. A hydrogen on a carbon double bond feels completely different electronic environment than one of a single bond carbon. Not gonna lie, I should look into it a little bit more. Now to your real question, how does this tell us how atoms are connected? Here's the key concept: electron shield. Hydrogen sitting next to an electronegative atom like oxygen has fewer electrons around it. Oxygen pulls them away, so it feels more magnetic field it absorbs. Each unique electronic environment equals unique absorption frequency, unique peak at the spectrum. So when you see a spectrum with four different peaks, you know there are four chemically distinct type of hydrogens in the molecule. So the position of each peak tells what kind of environment that hydrogen is in next, okay? The size of each peak tells how many hydrogens are in the environment. Take ethanol, the CH3, 3H far from oxygen, CH2, 2H next to oxygen, OH, H directly, each appears as a separate peak. I need a bit more explanation on this one. I kinda get that each hydrogen in different in or near different atoms gonna emit different signals, but I need more explanation on why the signals being different. Also, how is the C13 gonna be here? I thought most of the C in organic compounds are what? What? So, could you also explain the involvement of C13? Hmm. What? What's with that?
Hi Josh.
Yo, Devoto did. Appreciate you for checking out the stream. Submitting about a mixture. I did send the email. Hmm. I might get the reply today, maybe. I'm guessing. lab script, laboratory map, protocol. Yeah, there we go. Mm-hmm. Mm-hmm. Density measurement of the solid, mass of the empty cytometer, mass of the meter filled with water, filled with auxiliary liquid. Okay. Ebby. Okay. Preparative synthesis of cis and trans copper glycate, section 2. There's a temperature diagram. That's for section 3. Okay. Yo, now right now, bro. No, yeah, theoretical background, this procedures. It's a new one, right? Yeah. What's the green? Is it in CO2? What? I'm guessing that's not. Yep, I did know that. Oh, thank God. Thank God. I know that. Oh. Yes. Oh, that's good. That's good. Step in the right direction. Okay, that kind of removed a lot of stress from my head. The fact that the section 1 samples are not going to be thrown away. It's not me. It's not me. 20 minutes, 1 hour. I'll just read this and continue. Mm. Let me build this from the scratch. The core physics first. When you put a nucleus in a magnetic field, it either aligns with the field or against. To flip from low to high energy, it needs to absorb a very specific amount of energy, and the energy corresponds to a very specific radio frequency. The formula is simply conceptually. What? Simply conceptually? You reading, boy? It was simple. It's not simply. The fuck you reading? There's no point in getting angry. There's no point. Simple. The formula is simple conceptually. Stronger field felt by nucleus, higher frequency needed to flip it. Now here's the key. The nucleus never feels full external magnetic field. Okay. The electrons surrounding it act like a tiny shield, creating a small opposing magnetic field. This is called shielding. Okay, so more electrons around the nucleus, stronger shielding. Nucleus feels less external field, needs lower frequency to flip. Peak appears on the right side of the spectrum upfield. Fewer electrons around the nucleus, weaker shielding. Nucleus feels more of the external field, needs higher frequency to flip. Okay, I'm a bit confused on the flipping. Peak appears on the left side of the spectrum, downfield. Now apply this to your example. Example 1, CH3 next to your oxygen. Oxygen is highly electronegative. It pulls electron density away from the nearby hydrogens through the bonds. Those hydrogens now have fewer electrons around them, less shielding. They feel more of the magnetic field. They need a higher frequency to flip. Their peak shift left downwards. Compare that to a plain CH3 group, far from the electronegative atom. It has full electron density, more shielding, absorbs at lower frequency. Peak sits further to the right. What did I just read? Oh, Oxygen is highly electronegative. It pulls electron density away from the nearby hydrogen through the bonds. These hydrogens now have fewer electrons around them, therefore less shielding. Okay, they feel more electromagnetic field in the nucleus. Okay, they need a higher frequency to flip from this. Okay, their peak shifts left downfield. I don't know about the peak shift because I don't know what we're talking about. It's a full electron density, more shielding, absorbs at lower frequency, peak sits further right. This leftward shift due to electron withdrawal is called deshielding. Okay, you know what? I'll look into it next time. Now it's time to end the stream. And yeah, I got some calls, and we're gonna continue with lab preparation. At least section one. I don't have to redo section one. That saves a lot of time. Not gonna lie, people. Peace.